In the English countryside, along roads that predate the Roman occupation, there are wooden poles. They carry telephone lines now, fiber optic cables, sometimes nothing at all. But if you look closely at certain poles, particularly those installed between 1837 and 1880, you'll notice something unusual. The wood is thicker than necessary. The spacing between poles follows a pattern that seems inefficient for modern telecommunications. And occasionally, if the pole has been there long enough, you can see marks where something else once attached to it. These aren't just telephone poles. They are telegraph poles, and they tell a story about energy distribution that most people have never heard. Each one represents a decision about how to move energy from one place to another without the energy itself traveling through wires in the way we typically imagine. Let's start with what we can physically observe. In 1843, the Great Western Railway installed telegraph lines alongside their tracks between Paddington and West Drayton. The original poles from this installation no longer exist, but their replacements followed the exact same placement pattern. Engineers measured the distance between poles at roughly 50 to 70 yards, significantly closer than modern utility poles, which can be spaced 300 feet apart or more. Why the difference? The answer lies in what the telegraph was actually doing. It wasn't transmitting power in the conventional sense. It was transmitting information through electrical pulses, but those pulses required a specific kind of energy. Distribution that modern systems don't need. Telegraph systems operated on a principle called return earth circuitry. Instead of completing an electrical circuit with two wires, the telegraph used one wire for the outgoing signal and the earth itself as the return path. The electrical current would flow through the wire to the receiving station, deliver its pulse, and then return through the ground back to the source. This means the earth wasn't just beneath the telegraph network. It was part of the network. The physical evidence for this is still visible if you know where to look. At telegraph stations, many of which still stand as repurposed buildings. Throughout Britain, Europe, and North America, there are copper plates or rods driven deep into the ground. These are earth connections, sometimes called ground stakes or earth electrodes. In some locations, particularly in areas with poor soil conductivity, you'll find elaborate grounding systems. Multiple rods arranged in patterns connected by buried copper cables, creating what amounts to an underground antenna. The Smithsonian Institution preserves several of these grounding systems from 19th-century American telegraph stations. One example from an 1860s station in Pennsylvania consists of 16 copper rods arranged in a circle, each driven 12 feet into the ground and connected by a copper ring. The total copper used in this single grounding system weighs approximately 140 pounds. That's not infrastructure for a simple communication device. That's infrastructure for energy distribution through the earth itself. But here's where the artifact reveals something historians still debate: the efficiency problem. Telegraph operators in the 1850s and 60s kept detailed logs of signal quality, transmission distance, and system failures. These logs survive in archives at the British Postal Museum, the Smithsonian, and various railway historical societies. When you read through them, a pattern emerges. Signal quality degraded dramatically over distance, but not in the linear way you'd expect if it were simply a matter of resistance in the wire. Instead, the degradation followed patterns that suggested the Earth's return path was variable. Wet soil produced better signals than dry soil. Rocky ground was worse than clay. Proximity to metal deposits caused interference. One telegraph operator in Nevada, writing in 1867, noted that his station could communicate clearly with Sacramento during winter rains, but experienced significant signal loss during summer droughts. He attributed this to the Earth's unwillingness to carry the return. This is documented behavior, but what it means is open to interpretation. The mainstream explanation is straightforward. The Earth's conductivity varied with moisture and mineral content, creating an unreliable return path that limited telegraph effectiveness. This is why by the 1870s, telegraph companies began installing two-wire systems that completed the circuit through copper rather than the earth. But the physical evidence suggests something more complex was happening. In the 1850s, several telegraph engineers experimented with what they called earth batteries, systems that use the natural electrical potential between dissimilar metals buried in the ground to power telegraph lines without external batteries. The most successful of these was installed by C.V. Walker in 1841 on the London and South Western Railway. It operated for several years using only the electrical potential generated by copper and zinc plates buried in the earth. Walker's system wasn't theoretical. It was functional infrastructure that carried telegraph signals for commercial use and powered itself through the earth. The documentation exists. The patents are on file. Operational logs survive. Yet, earth battery systems disappeared from the telegraph network by the 1860s, replaced entirely by conventional battery systems. Why abandon a self-powering technology? The standard answer is practical efficiency. Earth's batteries were unreliable. Their voltage fluctuated with soil conditions, and they couldn't provide enough power for longer distance transmissions as the network expanded. But consider the engineer's own words. William Fothergill Cooke, co-inventor of the British telegraph system, wrote in 1856 that earth battery systems were theoretically sound but commercially impractical due to the impossibility of standardizing installation across variable terrain. Latimer Clark, a prominent telegraph engineer, wrote in 1868, "The earth battery's chief defect is not its power, but its independence. A network powered by earth potentials cannot be metered, regulated, or controlled from a central office." This raises a methodological question. What if a technology was replaced not because it didn't work, but because it couldn't be controlled? Between 1860 and 1880, telegraph companies systematically replaced single-wire earth return systems with two-wire circuits. This required doubling the amount of copper wire. In Britain alone, this represented approximately 15,000 tons of additional copper installed over 20 years. The expenditure was massive. Yet operational improvement, measured by transmission speeds, was modest. More messages could be sent simultaneously. But the significant change was centralized control. One telegraph engineer in 1871 wrote, "The earth return is like a river. It flows whether we direct it or not. The copper return is like a canal. We control every drop." The visible network became evidence of a choice about energy distribution, a choice between self-regulating energy flowing through the earth or fully controlled. Metered circuits, asterisk, asterisk, asterisk. The story continues where part 1 left off. The telegraph poles you see today aren't just old wood and metal. They are living artifacts of an energy philosophy that once prioritized, distributed, self-regulating systems over control and monetizative at the Science Museum in London. There is a small collection of telegraph insulators from the 1840s and 1850s. These simple ceramic knobs held wires away from wooden poles. But they weren't designed to prevent all electrical leakage. Early engineers intentionally allowed some current to pass through the wood into the ground. By the 1870s, insulators had evolved into double and triple skirt glass designs, engineered to prevent all leakage. The difference isn't subtle. It's a fundamental shift in philosophy, from systems using the earth as part of the conductor to systems isolating electricity entirely within purchased materials. Archaeological evidence confirms this transition. In 2003, road construction near Birmingham uncovered remains of a telegraph station that operated from 1845 to 1889. The foundations revealed an intact grounding system never documented in surviving technical papers. a central tinch copper rod, was driven 20 feet into the ground, with 8 copper cables radiating out to secondary grounding points, each with its own copper plate buried vertically. The total copper mass exceeded 400 pounds. This infrastructure wasn't necessary for a 2-wire network. It was part of a self-powering, Earth-return telegraph system. Radiocarbon dating confirmed the installation in the mid-1840s. Analysis of the copper plates showed crystallization patterns consistent with decades of low-voltage electrical current. The Earth had been actively carrying electrical energy for over 40 years. Even more striking, modern geological surveys have detected magnetic anomalies along early telegraph routes through iron-rich soils. These anomalies correspond exactly to documented 1840s-1870s telegraph paths. Sustained current through the ground created measurable, lasting changes in the magnetic properties of the soil. The Earth itself preserves a record of energy that once flowed through it. The implications are profound. Standard histories of electricity depict the telegraph as a primitive system replaced by centralized networks. But the evidence suggests a different story. A working, distributed system was deliberately abandoned for one that could be controlled, and Corporate archives show that Earth return systems required less copper, cost less to install, and were operationally comparable to 2-wire systems over moderate distances. Yet, by the 1870s, nearly all were converted to 2-wire networks. The stated reasons were reliability and reduced interference, but operational logs show modest improvements at best. What improved dramatically was centralized monitoring and control. Every electron could now be tracked. Energy became fully commodified. Modern HVDC transmission systems echo the principle of the Earth's return. In Sweden and parts of Canada, high voltage DC systems move gigawatts of power through ground return paths. The physics works. The Earth remains conductive. The principle scales to modern power levels. But for consumer distribution, 2-wire or 3-wire systems dominate, using the Earth only for safety grounding, not as an active conductor. The lesson from telegraph poles is about choices in technology. Infrastructure can be designed for efficiency or for control. The 19th century telegraph network shows that working systems can be replaced not because they failed, but because they were incompatible with centralized oversight. Visit a rural telegraph pole today in Scotland, Wales, or England. Some still carry modern lines. Others stand empty, relics of a forgotten philosophy. Examine the base. You may see a copper rod or cable disappearing into the ground unused, yet still capable. These are remnants of the Earth return systems. They are still conductive, still functional. They just no longer fit the model of control and monetization that shaped modern electrical networks. Even more broadly, the telegraph pole exemplifies a recurring technological pattern. Working systems that are difficult to control are often replaced by those easier to regulate, even when technical performance doesn't improve. From open protocols to subscription services, toll roads to highways, the pattern repeats. The choice isn't necessarily about what works best, but what can be controlled, measured, and owned. Ultimately, the telegraph pole is evidence of a fork in technological philosophy. One path led to decentralized, partially self-regulating energy flow through the Earth. The other led to fully controlled, fully metered networks confined to purchased conductors. We chose the second path, shaping innovation, regulation, and ownership of energy distribution for over a century. Yet the Earth return path still exists. The ground beneath telegraph poles remains conductive. The energy paths are dormant, waiting. The system could theoretically function even today. It was never physics that failed, it was our choice to abandon it. When you see an old telegraph pole, consider it more than an artifact. It is a monument to human decisions in technology. What to control, what to commodify, and what to forget. It reminds us that history is not only written in documents, but in the very energy beneath our feet. The poles remain, the ground remains, and the lesson endures. Efficiency isn't always the goal, control often is. Asterisk, asterisk.